Welcome dear students, we are on the CEC-UGC lecture. We are in the series of electronic circuit and we are discussing the various components of electronic which are used in the construction of the electronic circuits. In the last lecture we discussed about the antennas. What are the antennas and what are type of antennas and how they are used. In today's lecture we discuss the antennas efficiency. First, we know that antenna act as an interface between the electrical signal and the radio signals. Hence, the electrical signals are forwarded through the metal conductor and the radio signals are propagated through the free space. In 1886, first antenna device was developed by the Heinrich Hertz, and he has created the dipole antenna and with electrical signal, and he transmitted and received the signal. Now we discuss the antenna efficiency. Now what is the antenna efficiency? Any antenna is characterized by its efficiency. What is antenna efficiency? It is like the efficiency as in journal we use. It is the ratio of the power out to the power in. How much power it is out and how much power it is in, then we take the ratio of that. However, it is designated in the several different ways. In the most of cases, efficiency accounts for the 12R losses in any dielectric and losses based on the couple to the other devices. When we couple the antenna with other devices, then how much losses we have get, that also define the efficiency of the antenna. Now, what is the efficiency? What may not be included in any loss related to the antenna and the transmission, we will take the gain. The line mismatch losses resulting in the reflected power and a high SWR. Now in 1901, Marconi was the scientist sending the information across the Atlantic region, and the antenna parameters are more important in finding out the efficiency. There are the various parameters. Number one parameter is the directivity or antenna gain. Second is the antenna gain. Third is the resolution. Then pattern, antenna beam area, antenna beam efficiency, antenna efficiency may be defined like that. So we know the directivity, we know the antenna gain, we know the resolution or pattern of the antenna. We also find out the characteristics of the antenna beam area and antenna beam efficiency. The antenna efficiency denoted by the eta. Then we will discuss the complete information regarding the antenna gain. How much gain we can get through the antenna, that will define the efficiency of the antenna. Now, the ratio of the maximum radiation intensity of the test antenna to the radiation intensity of an isotopic antenna or reference antenna which is radiating the same power in total, that is the directivity. That directivity is denoted by the D. So, directivity of the antenna shows how it able to radiate the energy in one or more specific direction. Directive, that is related to the direction. So, directivity parameter of the antenna shows how much specifically direction a radiation have to transmit. Like the radiation pattern of an antenna determines its directive value. So, directive D defined by the maximum radiation intensity of the test antenna divided by the radiation intensity of an isotopic antenna. You see on the screen that here we are having a antenna type defined where we define the directivity, that maximum radiation intensity of the test antenna divided by the radiation intensity of an isotopic antenna. Now, the isotopic antenna is an ideal antenna which radiates its power equally or uniformly in all the direction in a space. There is no physical matter of the isotopic antenna and it can taken as reference antenna only. So, in other words, the antenna directivity can be defined as the ratio of the maximum radiation intensity of the test antenna to the average radiation intensity of the test antenna. Maximum radiation intensity to the average radiation intensity. Now antenna directivity D is equal to define as a D is equal to phi theta into phi maximum divided by phi average. Now we will see now D divided by the WR 4 pi, and D is equal to 4 pi phi theta phi maximum by WR. It is therefore the D is equal to 4 pi maximum radiation intensity divided by the total radiation power. So antenna directivity D, maximum radiation intensity of the test antenna to the average radiation intensity of the test antenna, and therefore D is equal to 4 pi maximum radiation intensity divided by total radiation power. So D is equal to 4 by total radiation power. Next, antenna efficiency. This is an important parameter of the antenna, and efficiency of an antenna is defined as the ratio of the power radiated in all the direction of the total input power supplied to its terminal. That defines the antenna efficiency. Due to the resistance loss in the antenna, the total applied input is not radiated to its targeted direction. So there must be a losses. So in the antenna efficiency, we define the ratio of the power radiated in all direction to the total input power supplied to its terminal. Now the efficiency of antenna defined by the eta. You see, the antenna efficiency can be known as the percentage. Also, when it is multiplied by the 100, the how much efficiency will define in the form of the percentage also. Usually the antenna efficiency factor lies between the 0 and 1. Antenna efficiency is equal to the power radiated by an antenna divided by the total input. Power radiated by an antenna, how much power an antenna is radiated and how much input we are giving. So on the given input, output power radiated, that define the antenna efficiency. Then eta is equal to PR divided by PR plus PI. PR is the radiative power and PI is the ohmic loss in the antenna. As we know that how much losses are takes place, how much input we are giving. So power radiated by the antenna to the total power input, that is the antenna efficiency. Antenna gain may be defined as the gain denoted by the G, and that is defined by the power gain GP, and by gain the antenna radiation pattern can be calculated. Antenna gain is defined as the ratio of the between maximum the radiation intensity of the subject antenna in the given direction to the maxima. Like the radiation intensity of an isotropic antenna when the same amount of power is applied to both the antennas. You see here T1, T2 and 3. The gain pattern is defined here by the 3 antennas. When the directivity converts to decibels, we can define it antenna gain. Now gain is equal to maximum radiation intensity from the subject antenna, that is defined by phi s, divided by the maximum radiation intensity from the isotropic antenna, that is phi I. So the gain of antenna efficiency into the antenna directivity D. So any gain of the antenna will defined by the efficiency as well as by the directivity. Gain is the maximum radiation intensity from the subject antenna to the isotropic, maximum radiation to the isotropic antenna, that will define the gain. When we know the efficiency as well as we know the directivity, then we define the total gain. What is the unit of the gain? The unit of the gain is the dB, that is dBi, that is the decibel, dB, decibels, dBi defined by the dBi, decibels related to an isotropic antenna, and dBd related to the dipole antenna. If it is represented by dBi, then it is unit of the decibel isotropic antenna, and if it is having a dBd, D in the last, then it is defined as the decibels dipole antenna. So this is the antenna gain, dBi and dBd, dBi for the isotropic antenna and dBd for the dipole antenna. When the directive converted to the decibels, we can define it as a antenna gain. and we know that again gain G is equal to maximum radiation intensity from the subject antenna, maximum intensity from the isotopic antenna. That will be the total gain. Then gain defined by the G, that also the antenna efficiency into the antenna directivity, and this is a unit as we discussed. The gain value indicates how much antenna succeeded while converting the input power into the radio waves in the specific direction. So direction is also important in the antenna gain. So it is very important in how much input we are giving and how much radio waves are converted and in a particular direction. How it converts the radio waves into the electrical from at receiver side. Sometimes the gain is discussed as a function of the angle. In this case, the radiation pattern is to be considered. On the basis of radiation pattern, we can define the directivity of the antenna. So antenna gain formula we define here. The gain value we can know how much amount of the signal boosting provided to the input by the antenna. It has the receiver stage, how much power required to reproduce the same transmitted signal from the channel. So gain of the subject antenna or the test antenna defined by GT is equal to GI plus I for the isotropic antenna plus 10 log 10 PT by PI, that defined by, now the abbreviation of the terms are that GT is equal to GI plus 10 log 10 PT PI, where GT is the gain of the tested antenna and GI gain of the isotopic antenna. So we are taking the tested antenna, so first we take the gain of the isotopic antenna plus PT, power radiated by the test antenna and power radiated by the isotopic antenna. In this manner we can get the gain of any tested antenna. Now antenna gain conversion, how we will do? Antenna gain is expressed in the decibels, that is a dB, because it gain expressed in the regular unit like in terms of the watt. In these cases, when calculating the received power, then the result will be very small. Sometimes it will give a exponential form also. Now it is hard to consider every time these type of values, so the gain can be expressed in terms of the decibel. Like if we are taking the 5 decibel gain, then 5 times the energy related to the isotopic antenna, and 5 times if decibel is if 5 dB we get the result, then it means the 5 times the energy related to the isotopic antenna in its peak direction of the radiation. So the linear unit are converted into the decibel by following equation. We know that P dB is equal to 10 log 10 P. Another unit of antenna gain is dBm, and M related to the milliwatt. It means the decibel related to the milliwatt. 1 watt is equal to 1000 milliwatt, that is 0 dB is equal to 30 dBm. Then dBi is another unit gain for the isotopic antenna. dBi means twice the power related to the isotopic antenna in its peak direction of the radiation. It will be the twice the power related to the isotopic. So the gain can be expressed in the units of the decibel or decibels milliwatt or decibels isotopic antenna, and mostly it is defined as decibel only. Then how we increase the antenna gain? At the receiver side we want the more power. So how we increase the antenna gain? The gain of any antenna shows that its ability to radiate the signal to the channel in any direction, and if the gain is more, such an antenna can be transmitted more power to the receiver side in a particular direction, and it attenuates all other signals from the other direction. So by maintaining the particular direction, we just get the more gain at the receiver side, more power output at the receiver side, and that must be in the particular direction, and all that can be attenuated from all the signals that are in the other direction, and that all focused on the particular direction, and the output should be maximum at the receiver side, that through which we can get the more antenna gain. If the antenna radiates the signal equally in all the direction, means it can possibly by only the spherical antenna, such is called as the isotropic antenna, and these do not exist in the real time. If we get we get a signal in all the direction, then that is possible through the spherical antenna only. If the gain is more, then an advantage of the circuit, but it's only depend upon the need. So what need we require, so on the basis of that the gain will be received. The following methods are useful to increase the gain of the antenna. How we can increase the gain? They must be effective. They must be having the effective area of the antenna. The effective area antenna should be justified so that the more gain can be received. So we can get the more gain in the parabolic reflectors also. Element array, reflector arrays plays also important role in getting the more gain. Antenna efficiency should be more, and directive is the one of the parameter to get the more output. The antenna is most useful in the field of the communication for radiating and receiving the radio waves through an electric form in the channel. Like it converts the signal into the electrical. There are the different types of the antenna. The types of antenna which are having the different structure from each other. On the basis of structure, on the basis of the parameter, on the basis of the gain, the antennas are defined. As per the need, they have used, and if the gain of the antenna may be low or high, that is purely dependent on the requirement or the need. How much input, how much output will be required in the gain side. If the gain is more, then it is capable of radiating the signal in the particular direction to the space. If the gain is low, it covers the wider range. And if we observe the daily communication system, we can get the more information about the importance of the antenna and antenna gain value. That will give the more information regarding the antenna, and antenna gain can be increased by the changing the parameters of the construction side of the antenna, like that we prepare the parabolic reflector in the antenna. So sometimes the element array require there, and reflector array also require, and antenna efficiency, directivity is the best part of the parameter, so that we can get the efficiency in a proper manner. So antenna play a very important role for transmission of the signal from one end to the another end in a efficiency manner. So the gain is important in terms that if the gain is more, then antenna efficiency will increase and it will perform better as compared to the another. We define the various type of the antenna, like patch antenna, like the dipole antenna, like the isotropic antenna, but nowadays we are using a more important side, that is the flexible antenna. These flexible antennas are used in the most of the electronic gadgets, as the electronic devices are miniaturizing day by day. So the antenna size is also getting miniaturized day by day. So nowadays it is a very great challenge to fit the antenna in a very small, in a compact or in a very small electronic gadgets, so that the signals can be transferred from one end to the another end. So for this, what is the efficient method so that we can get the good antenna? That is the part is the flexible antenna. That flexible antenna are nowadays used through the printing technology. That antenna are constructed through the printing technology or by other means to fit in the electronic gadgets. So the size of these antenna are getting small, as well as the efficiency are increased. The gain is also a one of the important parameter that will increase. The gain must be, and loss loss due to the resistance loss in the antenna must be less, more directive. So by keeping these parameters, flexible antennas are designed. So flexible antenna we will discuss in the next lecture. What are the flexible antennas? And now up to now we discuss the efficiency of the antenna by defined by the parameters. Number one is the directivity, defined by the antenna gain, defined by the resolution parameters, patrons, defined by the antenna beam area and antenna beam efficiency. So gain that will be defined by the antenna gain defined, antenna efficiency defined by the ratio of the power of radiated in all the direction to the total input power supplied to the terminal of the antenna. So due to resistance losses in the antenna, the total applied input is not radiated and to its targeted direction. So efficiency may be defined in terms of percentage, or sometimes is defined in between the 0 and 1. Thank you very much.